This straight line is the room temperature. In the hydrogen model, when we heat it, temperature increase, then approach a constant number theta F. For the deuterium model, we heat it, it approach another temperature. This temperature is always a little bit higher than this. And we change this heating power, it will go to different final temperature. So we can calculate the temperature difference between this number to the room temperature number. Then we list them in the following table. So this is the heating feature of these two systems. This column is the current in the tungsten wire increase this direction. This is the temperature difference between the final temperature and the room temperature. This is for deuterium, this is for hydrogen. At the beginning, this number is almost the same as this number, but a little bit higher even in the hydrogen model. But when we increase the heating power, the temperature difference increases much faster in the deuterium model than that in the hydrogen model. So at the end of this, the temperature difference is about 8 degrees higher in the deuterium model. If we calibrate it, it's about 0.8 watt. At the beginning, we worry about there may be something wrong in our system because the thermometer position may not be very accurate in between the tungsten wire and the palladium wire. If this one a little bit shift, may cause a temperature difference, just as Professor Ikegama pointed out also. We worry about this. Fortunately, there is a tungsten wire in the center of the system. It gives us the information for the temperature also. Fortunately, we have this number because in order to measure the power, we measure the current because palladium wire in deuterium model and hydrogen model are in series, so their current is the same. We measure the voltage on it, then we get the power. So the power is larger means the resistance of this tungsten wire is larger. So at the beginning, in the bottom of the hydrogen model, the tungsten wire is a little bit higher resistance. But at the end of this resistance is higher than this resistance. So we use the temperature coefficient for the tungsten wire to calculate what's the temperature difference between these two. It's more than 20 degrees. So we are sure the deuterium model is hotter than the hydrogen model when we heat them in the same about the same power. Now you may ask, if we do not heat it, what happens? We did this also. This is the time, this is the temperature. We measure the room temperature, that's the line here. This is about 1 week. Every day in the night, the temperature goes up, goes down, goes up, goes down. That's room temperature. And we measure the temperature in a bottle just filled with air. It follows this room temperature. The hydrogen model, the temperature follows this room temperature closely also. However, the temperature in the deuterium model is always a little bit higher, about 1 degree, without any heating. We still worry about this. There is some calibration problem. This temperature difference is constant maybe, because we didn't go to the right calibration. So we calculate the difference between the deuterium model and hydrogen model. This is the time for 1 week. This is the temperature difference between the deuterium model and hydrogen model. We notice that this difference fluctuating day and night also. temperature goes up, then difference goes up. But here we draw the thin line that's for the temperature in the deuterium bottle. You may notice that when the deuterium bottle gets the highest temperature, the difference is not highest. But if we calculate the derivative of this deuterium bottle temperature here, we get this green line. This is 0. So here is negative, here is positive, negative, positive. Then we may notice that the highest difference just get at this bottom. And the lowest is here, just the temperature change the farthest and up. So we may imagine there is an energy source in the deuterium bottle, and this source is proportional to this temperature difference with negative sign. This is just what I need for the fine-tuning mechanism. If the resonance happened in a very narrow energy level, we need some mechanism to lock them. Once they are in resonance, then a little bit heat, then we hope it will come back. I talked this on the first day. So this derivative negative sign just what we need for this fine-tuning mechanism. Now I go to the summary. The first, the gas loading system is a good way to find the temperature behavior for deuterium hydrogen system. And unexpectedly, use a piece of tungsten wire, we can maintain the high loading ratio for several months at the pressure less than 1 atmosphere. This is unexpected. Second, based on the calorimetric feature during the cooling, during the heating, we extract the information, the excess heat power in the deuterium bottle may be as high as 0.8 watt. It's equivalent to 3 watt per cubic centimeter palladium. If we do not heat it, just let it cycling with the room temperature, we get the information that this excess heat power is proportional to the temperature derivative with negative sign. And this is what we need for fine-tuning mechanism which supports the resonance penetration of Coulomb barrier, and which can explain heat after death, heat after life. More important, from this fine mechanism, we predict this fine-tuning parameter is real important. So I want to put my last page. This is a list for the fine-tuning parameter. This number is the volume of the palladium sample. This is the heat transfer coefficient. Here are two positive experiments did by Makoeto and Kunimas. In fact, I really need this data to persuade all the opponents in China. But later we found this number, negative. And this time during the conference, we heard that the mass flow calorimeter gave us the 0 result. Fortunately, now we found this parameter in his case is very small. He is using very small volume of palladium, and in order to improve his instrument, he used silicon oil to increase his transfer coefficient. Then this fine-tuning parameter for him is 20 times less than that in Dr. Makoeto's system. This time, just lunch, I asked Dr. Kunimas. He was so kind to tell me this number for volume in the mass flow calorimeter is about 0.28. And the heat transport coefficient, unfortunately, is very large in this kind of calorimeter. So this number is about 0.3. So this gives us a kind of feeling, maybe we need this ratio is in the range of this number. And let's look at Dr. Miles' experiment. He got very high reproduction coefficient. This is the volume. He is using 6 millimeter diameter palladium rod. And his coefficient is low with good insulation. So his number is the highest now available for me. Professor Freshman and Pounds did a very good experiment. Their volume is small, but their calorimeter is made of quartz. So their heat transfer is dominated by heat radiation. So this number is small. So his number is very close to Dr. Mercury. I got this number by fortune because in my system, this number is low, thin wall stainless steel dual system. And I use this number because I know I can tell only 0.2 watts in my system. So I get this large number. Then my number is fortunately high. The Lewis of Caltech is very small number, but they are Caltech, is very fine calorimetry. So their number is large enough. They are supposed to see the positive result. Unfortunately, it was reported as negative. Anyway, here can help me to figure out the number in the Wolf's experiment. What is his volume? What is his conductivity? Or you can communicate with him. Suggest him pay attention to this fine-tuned parameter. Thank you.
Yes, just on the last point, I mean, Lewis said he didn't have any excess heat, but those of us who've studied his work very carefully would say that he did have excess heat, actually. This question of heat after death is very interesting because, of course, in your system, you are perturbing the temperature. So actually not what Dr. Makoeto said this morning. Of course, you get a non-equilibrium, very high non-equilibrium negative potential by increasing the temperature. So this is something which possibly, why this particular point had not been taken much sooner. But if you now track through the heat after death episodes, there are not very many known, you will find that you really get this heat after death phenomenon if the temperature is high. So I think what you are really seeing is when you heat the wire up, when you heat it up appreciably, then you get appreciable heat after death. So there are two effects. You're perturbing, you're getting this rather high non-equilibrium chemical potential, and then you are maintaining, you're getting appreciable heat generation in the system, which is really like the heat after death phenomenon. I recommend you to study the work I've always taught you, Ikegama mainly, which is really very important in this area.
Thank you very much.
I think it should be better to try and have a simple explanation rather than ask for a miracle. It looks as if your apparatus, the insulation, the thermal insulation is not outstanding. Would you consider repeating the work of Imura, Japan, with a very nice calorimeter, with constant temperature, and a large water system outside? The idea is you have constant temperature, so you know where the heat flow is, and I think this might simplify things. Secondly, I mean, have you taken into consideration the different thermal conductivity, convection of hydrogen material? Is there a difference?
I think if there is any difference, it will show in this line. At the beginning, I do not know which one, I did not know which mechanism is dominant in this system. After a calculation, I know the dominant is heat conduction. If the temperature is higher than 80 degrees, then the heat radiation will come in.
How do you know it's heat conduction, not convection?
Based on this Newton conduction law.
But that doesn't contain radiation.
Radiation is different.
is the second best means of transferring heat. Hydrogen gas is the second best means of transferring heat after diamond.
So it's conduction, that's
Convection.
Radiation. If it's the second best means of transferring heat, then it's not going to be radiation. It consists.
No, it's mainly convection, but there's also radiation. But convection, I think, is a worry. I think one should worry about it.
Please notice this law, Newton conduction law, dominant in this case. At first, I list a lot of terms there. I try to check whether they are important. But when I get this straight line, then I feel released. Am I answering your question?
Yes, I was wondering how you measure the temperature inside your chambers. Specifically, could it be that there's a slight effect of your temperature indicator on a kind of gas? I didn't hear how you measure your temperature.
Okay. That's very important. If I were to do something, improve my system, I will do this. Right now, only one service, platinum thermometer in it. I just measured the resistance of this platinum wire. It's about 100 ohms. So I'm using the Kisley digital multimeter from the United States. So it gives me very accurate number for this.
Accurate measurement maybe, but PT does absorb D and H, and that would probably change the resistance slightly, and therefore the calibration factor, and that it could be different between D and H, and that may explain your effect.
Thank you to remind me this point. In fact, I'm using a platinum thermometer is specially made for this kind of purpose in the gas. It's sealed by a ceramic. All this thin wire, just like a needle, and it's sealed in a ceramic tube. So I'm sure there is no this kind of thing. Yeah.
Earlier in the day, I showed data that proves that a thermistor, thermocouple, tungsten helium wire furnace are hotter in one gas and another gas with the same power input. Now, deuterium has a lower thermal conductivity. I don't care what the mechanism is, it has a lower thermal conductivity overall than it does hydrogen. And therefore, the thermometer, I don't care what it is, and your tungsten wire that heats is are at higher temperatures because the deuterium is conducting heat less. Unless you eliminate this problem, I cannot believe you.
Thank you. This is important. I worry about this also because the mass for the hydrogen and for the deuterium is twice different. So their heat conduction coefficient should be different. However, in my system, the dominant role is the thin wall of the stainless steel dual. It determines the heat conductivity. So any difference in the heat, gas, that's a minor. If you look at this slope, they are a little bit different. This difference may be explained by your effect. You see, this slope is a little bit smaller than this one. This just means the heat conductivity is a little bit smaller in the deuterium system. Maybe I'm wrong, I'm not an expert in this area. But I worry about this also at the beginning.
Use a CMake color in there.
I have no money.
Okay, now, everyone satisfied? Thank you again. So, we would like to close the general presentation now. So still, we are no break and continue to do.
Thank you very much. We would now like to proceed to the final part of this conference and would like to ask Dr. Bressani, Dr. McCurry, and Dr. Ikegama to give out a summary for this conference.
Okay. You hear me? Yes. This is the layout of my comments. And a comment of the comment is I am very much happy of giving my comments now that when I was asked to do, because in fact I was not expecting to have at this conference such interesting results on nuclear products. Now, let me start with some remarks that everybody knows that from the beginning of the qualification story, all of us were really struggling with two main problems about field. One is the reproducibility. The second one was the nuclear origin of the observed excess heat that sometimes were observed by the different groups. And the hypothesis of the nuclear origin was put forward just for the big amount, being not possibly related to chemical effects, atomic effects. Now, at the time of this conference, my opinion is that a positive answer was given to the second point, that the sometimes observed excess heat is of nuclear origin, and my opinion is based on the assembly criteria that everybody of accepting that we have several independent confirmation by different labs. Now, let me very briefly remind what was the question of the nuclear ashes from the beginning. First paper of Fleischmann and Pons, they said clearly that the neutron and tritium production that are the obvious candidates to be the nuclear ashes from the known DD reaction in vacuum. They were, even if measured with very poor experimental methods, were absolutely not able to observe, to explain the observed excess heat. They were lower by 10 to the 8, 10 to the 10, it depends on different measurements, orders of magnitude. And so, just in the beginning, in the first weeks or months, it was put forward the hypothesis that some other reaction, in particular a reaction leading helium as a final product, was the responsible of the excess heat. And I only remind that there are just at the beginning some theoretical explanation on that. Now, like experimentalists, we can ask why, even if Fleischmann and Pons said that there were very few neutrons, very few tritium, most of hundreds of groups immediately rushed to measure neutrons and tritium. Sorry. The answer is very, very easy. There were plenty in all the labs, region 4, there were plenty of neutron detectors, plenty of tritium measuring devices. People knowing how to do, essentially physicists that are eager to enter into the field of fusion. So immediately there will be a rush of people doing experiments on neutron and tritium. Why? Clearly in the hope of measuring clearly a nuclear rush without any doubt coming out of the cell. Clearly, what was happening, that the experiments, all the experiments has more or less the same hardware. The emission is very weak, is very weak, if observed, and the signals, as we know from the last 7 years of experimentation, and as we have seen, even now, there is in the order of some sigma on the data. Now, even if it was anticipated that helium-4 could be the responsible of the heat, you can ask why it was not measured. The answer is very simple. The methodology of measuring helium-4 by mass spectrometry is very difficult. Very few people know how to do about it, and even more, there is no commercial device that people could buy if you try one. Now, let me go to the main part of my short talk. Here, I am showing the historical trend of the helium measurements. Look at the pointer. I put here on the abscissa scale the time as measured by the different international conferences on cold fusion. So starting from the March 89, we know that there is the average time among one conference and the other is 115 months. And so at Salt Lake City, no measurement of helium were done. At Como, a very important measurement was presented. It was a kind of experimental milestone. In my mind, is the milestone of all the story of helium measurements. And those continued to present results at all the different conferences, including that one. At Nagoya, we had another presentation of helium production by Yamaguchi that unfortunately I say is around and called a sort of desaparecido because he, of course, he did a very impressive measurement at the time, but after he stopped it, and I know that he's preparing some other experiments, so I hope that it will appear at ICCF-6. At Maui, we have another experiment coming, and there is also another important event at Nagoya. It was Ulvac presented a commercial quadruple mass spectrometer, which was more and more used by several people. At Maui, there was another very important experiment of Rome, done by Gottfried. And let me mention that both the mice experiment, both the first generation of Gottfried, were done by existing spectrometer, mass spectrometer, far away. For the case of mice, a little bit not so much far away, but certainly not online in the case of Gottfried. At Monte Carlo, you see from here you see the effect with the two conference delay, the effect of the vulva. We show up for our preliminary results on helium detection. And now, as you see, we have a considerable, in total 6 experiments reported on helium-4. What is quite important in these experiments, and I will comment very brief, and I'm trying to explain with different colors. Out of the experiments, 3 are studying the electrolytic system, and they are doing correlation between heat and helium production. 2, Yamaguchi and us, we are using gas loading, and we are not giving a correlation with helium. And there are these 2 last experiments, which all these experiments that I mentioned up to the last give clear evidence, signal correlation of big production of helium-4. These 2 are still, I'm calling it young experiment, so they are not definite answer about that, but certainly they are not saying there is no helium. Now let me briefly comment on the experiments, starting from what I call the milestone. Mice give here a final report after 7 years of experiment. in which he did a big amount of different experiments, succeeding, not succeeding, to produce excess heat. You know, we heard from him all the story about the catheter and so on. We heard also from him that he has to carry out the experiment in a very hostile environment. And at the end, I think the very important point is that he gets a positive correlation between the helium measured and the heat in 30 over 33 of the experiments. And this will correspond of a random correlation of less probability of random correlation less than 1 million. Now, let me pass to the second experiment, which is their own experiment of Gozzi, again done by electrolysis. And I must say that on all the experiments that I've ever seen that were used to this, by the way, certainly the most, of course, always my impression, the most complete and performing experiment. Gozzi and company, they have everything. They have color imaging, they have neutron, tritium, for X-ray detecting online, which is something that most of the people did not have. They have a careful control of the atmospheric contamination, because one of the troubles that exists in the helium measurement is some leakage of the system and some helium entering. And what they have is, when I speak of correlation, I say that I must clarify that there are two kinds of correlations. One correlation that is that one by all the experiments, it means correlation blank or blank. In the blank measurement there is no helium, there is the blank experiment, no helium. In the active experiment there is helium commensurate to the heat which is reported, and this is the usual correlation. What the group of Rome is doing something which is rather more sophisticated. They are trying to do it. They are doing a time correlation, which all the other experiments, or at least part of them, they are not doing. It's trying to correlate the excess, the temporal evolution of the excess heat with the temporal release of helium. Now, I have no much more time, but I will simply flash an idea of how performing is the experiment of Rome. This is a 4-cell, practically all this part is duplicated, is relevant to each cell. A big amount of work was devoted to study the temporal evolution of the helium detection following, because it's a sample detection in a given after some elements. And this shows the correlation among the heat release, and here you don't see, this is a, sorry, this is the heat release is that one that is supposed to be, you had a problem on the printer here, and it is shown here. That blue curve is what, well, first of all, the correlation, the standard correlation on-off was clearly seen by them. Now what I am showing is the correlation, which is not, it is but less clear, the time correlation. Here we is the amount of helium that would be expected by the characteristics of the apparatus, and here are the experimental results. Now from that, the authors deduced, well, I have no time of entering the details, a ratio among the helium that was measured and helium was calculated, and unfortunately they did not show up here, and I cannot put one over the other because there is scale different. Which was the heat evolution? Well, the heat was like that, like that. So there is a partial correlation, time correlation, not a complete time correlation. But well, again, they were also very, very interesting. The finding of the X-ray online measurement, in which they showed this spot structure. They observed the spot structure and in particular the energy which was certainly larger than the normal, the K alpha line of alert, again, which is a clear demonstration that you have X-rays, this electromagnetic radiation of non-atomic origin. Now, let me go again, let me go ahead. And another measurement that was, this is apparatus performed constructed by us with gas loading. It was, I think that the main merit of this apparatus is to be completely stainless steel, so avoid all the problems of contamination, no glass contamination from the atmosphere. And by using the electromigration, we observed a quite clear signal of very clear signal of helium production after several days of loading. This was the spectrum measured by the spectrometer before starting the loading, and this is the spectrum that we had. That's the end of the experiment. And the amount of helium will correspond, this peak corresponds to about 5, 10 to 18 atoms emitted by the sample. A very impressive, now let me go to the other experiments. A very impressive measurement was reported by Professor Arata. Again, it was electrolysis, very well controlled. And again, he presented big amounts of helium released from palladium cathodes that were melted after having produced heat. And it was a clear-cut correlation with the excess heat that was shown. Let me simply flash the results of Professor Arata. Here, the excess heat he was obtaining was the electrolytic cell with the closed electrolytic cell. It was a very clever sampling device in which he has two. It's the only experiment using two QMS with the sampling device, getter pump, molecular pump in a very intelligent configuration. And the results that probably all of you have seen are what Arata wanted to demonstrate is to discriminate the helium which was emitted by the sample by and which is well resolved by the mass spectrometer with the action of the getter pump. And to do that also he compared on the contrary for helium-3, the spectrometer is unable to distinguish among helium-3 and DH, which is certainly is a contaminant that is present in a big amount in the gas sample. And from this time spectra, it was demonstrated in a completely clear way that at the end, having this trend curve of helium, only helium was produced. Now there are other two experiments here that I am calling young experiments in the sense that they were just starting. It's the experiment of Takahashi, which is quite complete. We flash here the setup, which is again an electrolytic cell with closed electrolytic cell with measurement of neutrons, and what we are measuring online is neutrons and the loading ratio. Offline we are measuring helium-4 and tritium, and the preliminary results are in this table, contained in this table. You can see that they have a correlation but with some interrogation points because they say they are not yet clear from the calibration. And finally, the last experiment, which was reported is by Tiki, Ikegama, again electrolysis, again an experiment with calorimetry, neutron, helium-3, helium-4, even X-rays. And in this case, they have one event of helium over heat production, but they will not succeed in observing helium. That is their apparatus. But I think that they observed helium after heating, but they have doubts about possible contamination. Again, is a sort of young apparatus, so they said they have to learn how to run it. Now that is for the, I think, is convincing evidence of the helium production at a rate which is expected by the heat. And so I will not say practically nothing about the correlation on neutron emission on excess heat. Of course, since the neutron emission is weak, you know, there is even to find a correlation, it's not simple. And okay, we had two examples here of correlation, one from Sanchez, one other from Okamoto, and okay, we see that even if weak, there is some correlation among the excess power, and this is the transparency by Okamoto. Now, let me go to the conclusion. The conclusion is that we observed heat largely from 5 experiments. We have the report of a large production of helium-4, quantitatively compatible with the with the quantity of the excess heat, which is declared by the different experiments. This was done by 5 different experimental groups, and 3 of them, this group, reported clear-cut correlation among helium and heat. So, in my opinion, the experimental facts are largely enough to conclude that the energy released is a nuclear energy, so is the DQ3 reaction leading to alpha, a helium-4 plus. And again, to conclude that the claims of Fleischmann and Pons 7 years ago were correct, and what the only thing that probably they were not so much correct is the time scale that we were anticipating for the reproduction of the result, for the confirmation of the result, probably of factor 5. Now, I'm going to my conclusion. Okay. Is the future of the measurement of helium-4 with QMS, which is still quite difficult, and we are the people that are not doing such experiment probably they have to enter into the field before for understanding all the problems that they are. There is plenty of pitfalls, but I think that we have to meet together in order to normalize the procedure, because we have different conditions, whether we have the pumps, the turbomolecular pumps working, not working, the effect of the getter pumps, the determination of the sensitivity of spectrometer, the residual pressure, and so on. So we have certainly to meet together to find agreed protocols and to arrive in a certain sense in a situation like that of the loading. I remember that when at Salt Lake City there was some erratic determination of loading, was asked a protocol on loading. I think that we have now to do the same. And I strongly recommend the group that have, it's not only a question of money, but certainly also a question of time, to learn how to use this object, to use helium-4 detectors instead of neutron detectors as routine tools in cold fusion experiments, perhaps arrive to a possibility of making calorimetry by helium-4. And my conclusion is I feel that it is quite possible, since we are speaking simply of normalizing, of talking each other about the experimental procedure, how to normalize billions of particles, not billions of dollars, like it happens several other times in human experiments. So probably an agreement can be found rather easily. And so I hope this pure scientific and experimental discussion will go ahead after this meeting, and perhaps we have to organize a workshop on it, finding a volunteer. I think that we have. Thanks.
Well, most of you know me as a scientist, so I thought I'd introduce you to my talent as an artist. Limited. I must say I'm rather pleased with the results of this conference. I see a number of very positive things. I think the fire that was fueled by a fever of enthusiasm from the beginning and has sustained many of the people in this room has sort of resolved itself into a seriousness of purpose, and that came out very, very clearly in the conference this week. Partly, I think, because many people have accepted the answer to the existence question: is there a phenomenon, is there not a phenomenon? I think it's clear that there are phenomenon, is a phenomenon, there are phenomena which we must explain. I think we explain them first to ourselves, and then we explain them to the world. With respect to nuclear products, Hideo gave a very good overview of the helium-4 results. Very impressive results. All of the workers in that field are to be commended, and if it turns out that the correlation between helium-4 and heat stands the test of time, Miles and Bush and Legalski are going to deserve an awful lot of credit. Tritium, two significant results reported here, or one sort of reported here. The report by Ed Storms of Tom Claytor's work, very, very impressive, very interesting, very hard to argue with, clearly nuclear in origin. And Dr. Ramadanov got to present a little snippet of his work. I'm much more familiar with it. I've been to his experiment, seen it, sampled the gas and analyzed the tritium in it. It is a very impressive piece of work which very closely conforms to the results that Claytor is obtaining. Transmutation products, I think, are the wild card in more ways than one. I just don't know how to assess the transmutation business. It's already spinning off mini conferences of its own. Should that work hold up, it will certainly evolve to dominate future conferences. Heat, on a very rough count, I found more than 20 groups reporting heat, either in oral sessions or posters here. Different experiments, different experimenters, different techniques. The robustness of the heat observation seems to have achieved to the point that we're not talking about whether there is a phenomenon, but what the phenomenon is. The issue of replicability, however, is severe. Neither the nuclear products nor the heat are attainable under sufficiently well-defined conditions that we can guarantee to produce them on any given day in any laboratory over any period of time. Serious problem, both for the nuclear and heat communities, which are in fact quite obviously the same community. What I've suggested is that there are a lot of, one at least, perhaps two, perhaps more uncontrolled variables. I think of this as a process with a transfer function. There's an input state. The input, in my mind, is a piece of palladium into which one is putting deuterons or other species, but temperature, composition, time, some of the variables we know about. We've identified some important variables, but the variables we've identified are clearly not enabling, as Storms put it. There's also a process, a mechanism. After our input, there's some process. We get the output, heat, and nuclear products. Somewhere in this step are some hidden variables, and the theorists really have to help us understand what those variables are and where we might begin to find them, to explore them, to control them. Tulio really concentrated on nuclear products, and my field of expertise and interest pretty much is in electrochemical heat, the generation of excess heat from electrochemical systems. This particular branch of the field is what started it. It's what has entertained most of the research interest. In my view, presumably the most significant in any commercial sense. And I want to talk a little bit about what has occurred to me at this conference, and what had occurred to me before, the mass flow calorimetry problem. You heard the results reported by Mr. Kubota of the IMRA Japan effort. To my shame, I would say that the work done at IMRA Japan is probably the most systematic attempt to explore this generating function. They've done a more systematic, more extensive effort in exploring the input variables to this function than we have. The results in 32 experiments, I think, no excess power. The new Hydrogen Energy Labs flow calorimetry system, an exquisite calorimeter, beautifully engineered, no results. SRI, we certainly have somewhat of a paucity of results, and I could certainly bring you any number of null results, all in good mass flow calorimeters. Why is that? It's a worry to me. Remember the function, excess power is some function of what I call excess loading, d to PDO to some ratio, excess current, to get to a large perturbation level, and flux. I should remind everybody, Professor Okamoto was kind enough to use this function, others have described it. This is a very tenuous model, but let's suppose that the model is right and explore what might be happening in these various flow calorimetry systems. First thing is the data of Nakata and many other authors, and Kunamatsu presented, I suppose, yesterday. Some of the work, their highest loading work, just looking at the first factor in this, the highest loading work is with palladium rhodium. This function doesn't have anything to say about palladium rhodium. I have absolutely no idea how it should behave, how it does behave, how it will behave. Clearly, since hydrogen and deuterium load so easily into palladium rhodium, the activity, which I believe is the important variable, as I've already said today, and Martin Flashman has reinforced, the activity of hydrogen and deuterium inside a palladium rhodium lattice at the same value of X is much lower. So I don't know, I have nothing to say at all about the loading, the very high loading levels obtained by IMRA Japan, palladium rhodium, and their failure in that system to observe excess power. One thing I did note, and I would call to your attention, and this is not a criticism in any way, IMRA Japan have their own resistance ratio versus palladium loading functionality. Now theirs may be right, and mine may be wrong. I've never claimed to have calibrated that function pretty well, but in order to convert resistance ratio to loading, we all have to use the same yardstick. The yardstick is already not straight, but if we calibrate the yardstick differently, we're going to find it very difficult to trade the results. So when they have converted their resistance ratio to loading, they get different numbers than I would get converting resistance ratio to loading. So the plea is either agree on a functionality, whether it be right or wrong, but let's stick to one, or express results solely in terms of resistance ratio on the right-hand side of the maximum, which I prefer to do. If you do that, you find that the loading levels that they've obtained are not all that spectacular, certainly not as great as one would have guessed from the
stated loadings given to us by Dr. Nakata. But I don't know about that. There's loading, there's current. The variable here at the end is again the wild card. Dr. Chelani made a point, a very good point. We need to depart from the steady state. I believe this. In a mass flow calorimeter, the most sluggish and stable of animals, it's the hardest thing to do is to depart from the steady state. Very difficult to do. What we've done in part, and partly in response to our critics, is to make our calorimetry in such a way as we improve the data quality. You improve the data quality by averaging things for a long time, never changing anything, so that when you present your data on a view graph at a meeting like this, the line is very clear and there are no little irregularities that you have to explain. In doing that, of course, you maintain the system as closely as possible in its steady state. And we really engineered and designed our system to do that, and that's what flow calorimeters do well. I question now whether that is wise. Another thing which we had done in previous years is measure our resistance ratio by passing a rather large current pulse, or a sequence of current pulses through the cathode. So we were performing electromigration experiments, which was some sort of departure from the steady state. The take-home message that I have had from this conference, that I will go back and act on immediately, is to reinvestigate, in our case it will be reinvestigate electromigration effects. We have started on this several times, found that it's very difficult to do, and given up. Electromigration is sometimes called the cone effect, passing a very large current through the axis of your palladium wire. Helps you in all of these things. It helps you in excess loading, and you get a chemical potential increase, at least locally. Obviously, it's current, so if current plays a role, you're giving it all the current, giving the system all the current it needs, and it imposes a flux. It also does what Martin Fleischmann and Stan Pons have exhorted us to do: load it and raise the temperature. You can pass enough current so that you actually increase the temperature. So for every reason I can think of, electromigration effects should be explored. I wish I had the courage of Giuliano Preparato. The experiment that he described is one that I would never have countenanced. I cannot imagine putting so much voltage into an electrochemical cell. My threshold of pain and fear is much too great. I'm glad that he's done it. He's shown that it's possible and stable and presumably safe. I might think about going back and doing it myself. Thank you.
Well, after these two excellent summary, very little left for me for summary. So that I like to give you just a short my personal impression of this conference. First impression is that finally I thought this Cold Fusion Conference grown up to the level of normal scientific conference. Thanks to you. And also appreciation is particularly to technical paper review committee chaired by Dr. Takahashi, as well as the organization committee chaired by Dr. Okamoto. My second impression was, or is, I was wondering what sort of view I can get after this conference. And there are so many stars and contributors, and I've been wondering what is behind this, scene. And very hard to guess what it is. And well, after this conference, my impression is that we will see what is behind this in 1 or 2 years. That is, well, staying in this hotel, actually, this is what we saw. We'll find out what was the cold fusion, or what is a cold fusion, within 1 or 2 years. So that I'm very much looking forward to the next meeting. And the third impression is that, well, I'm very pleased to find and to know that there are many byproducts from the wake of cold fusion activities, so-called, like high-loaded hydrogen metal material physics, like super vacancy state or super lattice structure, Peter's phonon lasers, or maybe related to hydrogen metal. And the electron migration is a very interesting idea. And also solid-state nuclear reaction. And transmutation or adhesion or hydrates. There are many interesting looking byproducts. So I'm looking forward to how these concepts develop along cold fusion activities. And I don't know what that cold fusion mountain is. But anyway, what I'm saying is we will reach there and find out what that is in 1 or 2 years. And this is just my personal impression. Thank you very much.
Thank you very much, Dr. Bressani, Dr. Makubri, and Dr. Ikegama. We have now come to the end of this conference, and finally we would like to close by asking Professor Makoto Okamoto, the chairperson of the local organizing committee, to present the closing remarks.
Good evening. Before opening the closing remark, closing ceremony, I would like to say a few words, all of you. As Professor Ikegami said, will introduce in his closing remarks, we have made so many efforts for a long time to this conference to be scientific conference, truly. So, we had several trials to follow. One is, we should carry out very severe paper review. So, I don't know, fortunately or unfortunately, more than 40 applications was cut off from the basing on the conference scopes. This work was done by technical program committee, international. Okay? And second, we changed a little part of this conference name. So this conference is not ICCF-6. This conference is the 6th International Conference of Co-Future. This is the second part. And third, we set up sessions, as you know well, from the first session, heat and fuel, and the last session is nuclear and heat, something like this. And also we have special session in night sessions, as you know well. Please understand what I want to say you. So, I now open the closing ceremony. First, I would like to thank to the members who strongly supported and completely supported to our conference. Please.
On the start.
Mr. Matsui, the secretary of this conference office. Linkage company's staff. And also the staff from my laboratory, the students, and LH laboratory in Sapporo, and Matsui-san's staff. And this, they were most important gentlemen, because we can enjoy very much this nice grand hotel. They serve us everything. So thanks again. One more ceremony I have. So, じゃあ呼んでください。
And now we would like to call to the stage the following participants to come on behalf of all the participants. So I would like to call out their names, so would you please like to come up onto the stage. Dr. Heinrich Hora, Dr. George Voronchan, Dr. Joseph Gruber, Dr. Georgie Eggley, Dr. Guido Gilli, Dr. Kyun Suk Yoon, Dr. Irina Savatimova, Dr. Carlos Sanchez, Dr. Suekai Chen, and Dr. Kenichi Yasuda. Please. And I believe, as this is the closing ceremony, I believe that Professor Okamoto would like you, each of you, to say in your own language, goodbye and see you again.
Я хочу сказать большое, огромное спасибо всем организаторам этой конференции. Я хочу сказать, что я очень счастлива видеть всех в этом зале. Я хочу сказать, что очень благодарна за ту возможность, которую я получила участвовать в этой конференции. Спасибо большое.
This is in Hungarian. Viszontlátásra.
Goodbye and regards from the kangaroos.
This is Italian. Only one word. Ciao.
This is German. As an economist and a statistician, I am a very rare element in this distinguished society. Auf Wiedersehen.
We say adios, hasta pronto.
저기엔 안녕히 가십시오. 다시 만납시다.
Moscou.
Thank you very much. I want to study English well. 日本語ありがとうございました。さようなら、また会いましょう。さようなら、また会いましょう。
Thank you. And Professor Okamoto has a small gift to all those participants on the stage.
I want to give this very fine souvenir to all of you, but our economy is not bad. So please understand me. So I would like to say again in Japanese. さようなら、また会いましょう。
Maybe also introduce to Professor Okamoto.